welcome everyone once again to the Melbourne Data Viz meetup. I'm excited to introduce Peter Goodin. He's going to be talking about a quick introduction to working with medical images. And so just quickly, I'm going to read you a little bit about Peter. Peter is a senior cognitive data scientist with HitIQ and was a stroke neuroimaging research fellow at the Royal Melbourne Hospital. They have over a decade of experience working with people data of all kinds, and their current career highlight was running a condom study. They also play guitar very badly. So welcome, Peter. Just going to stop my share and let you jump on.
Okie dokie. Thank you very much, Ned. And all right. So I think the standard question whenever doing this nowadays, can everyone see my screen? Fantastic. All right, so tonight I am going to be doing a very, very quick introduction to working with medical images in Python. I say quick because there are entire university courses devoted to this, and somehow I'm going to jam pretty much like a year or two's worth of information into the span of about 40 minutes, possibly 50. So the presentation is going to be in two parts. The first part is sort of a more tutorial type, just to get you a little bit more comfortable with what this sort of data is that we're going to be working with. And then the second part is just going to be what we all came here for, code and pretty pictures. So when I talk about medical images, what I'm really talking about is a sort of umbrella term for methods that allow us to visualize the human body and just allow for physicians to conduct examinations for a diagnosis of various pathologies. Medical images themselves can be acquired using multiple sorts of modalities. So for example, we can use electromagnetic radiation to collect medical images. There have been wars fought on less, but I will happily say that I'm a firm believer that EEG is a form of medical image because it contains spatial information. We can also use sound to collect medical images and ionizing radiation, so positron emission tomography and X-ray/CT. This evening, I'm going to focus very much on MRI, but a lot of the things that I talk about are actually able to be applied to modalities such as CT, and also for things like MEG, so magnetoencephalography, EEG, electroencephalography, and NIRS, so near-infrared spectroscopy, largely because they also, to a certain extent, deal with three-dimensional images of the brain. So as Ned so very nicely introduced me, I am currently a senior data scientist at HitIQ, where we're developing a smart mouth guard to help monitor professional athletes and gauge their risk of having a concussion through impact. But prior to that, for 15 years, I was in the wonderful world of academia. I got my PhD in psychoneuroimmunology, which, as the joke goes, I received the PhD because I was able to say that without flinching. But previous to sort of becoming a data scientist, I was fortunate enough to work with multiple forms of medical imaging, so MEG and MRI and EEG. I spent 2 years working with CT, so computerized tomography at the Royal Melbourne Hospital for stroke diagnosis. And also my claim to fame is currently running a study that's that looked at neuroimaging correlates of condom sensation. It was academically good fun. So for those of you who are unfamiliar with what an MRI looks like, it is this great big machine here. As you can see, a patient is put into the gurney and then popped into the machine, which contains a very, very high magnetic force field. Now, discussion of the physics behind image acquisition are really, really quite out of the scope of this talk. So I've kind of aimed this so it's quite all right to just understand that it's a very big, very expensive machine that goes bleepity bleep 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 for about 5 to 10 minutes or however long the image acquisition goes for. And then at the end, out pops a very nice, pretty picture like the one we can see on our left here. So this image that we can see on our left is actually, as you might guess, it's an MRI image. It's taken an image of the head, and it's basically a slice which exists sort of between the two ears, like the front of the face has been sort of sliced off. Looking closer though, we can see that this image is actually made up of a huge amount of varying teeny tiny little squares. Now these squares have different intensity values to them. So the lighter ones have a higher intensity, the darker ones have a less sort of intensity, understandably. And these are actually not squares, but cubes, specifically voxels or volume elements. And each one of these voxels contains a single value, which represents the intensity of that particular voxel. Now, the image itself is made up of sort of sheets of overlapping tabular data, if you will. So basically, if you've worked with spreadsheets or data frames, which I'm sure pretty much everyone here has, what we can think of is it's basically just a whole bunch of stacked data frames or spreadsheets on top of each other. And these, when combined into a matrix, allow us to generate the nightmare fuel image that you see on the right, which is an MRI image in 3 dimensions. Very quickly, voxels themselves can contain multiple kinds of information. So the one that I'm going to be talking about tonight is going to be, it just contains a single value. And this single value voxel is typically part of a group of MRI types called structural images. On top of that, we also have voxels which can contain time series. Although more specifically, it's not really a time series trapped within a voxel. It's more that the time series represents the flickering of voxels over time. But for simplicity, we'll just say that it's a single time series trapped in a voxel. And that is representative of functional MRI or fMRI, which I'm sure everyone knows with those nice pretty pictures of blobs on brains. Also, voxels can contain directional information as well. And so that directional information is usually within a particular class of MRI image called diffusion imaging. And that's very largely looking at tracing the white matter of the brain or the telephone cables of the brain. And that's associated with a couple of different imaging types, for example, diffusion tensor imaging or pixel-based analysis. But once again, tonight I'm going to talk specifically just about structural imaging, or even more specifically, just T1 weighted images. So that is a very brief introduction to sort of to medical images, or specifically MRI. But tonight what I'm going to be doing is trying to take us all from the very standard sort of, you've just gotten some data off a scanner, all the way through the pre-processing up to, right, now I have my data, which allows me to do fancy things like group comparisons or regression or classification, that kind of stuff. Along the way, we need to do several things to the data. So I'm going to be reading the data in with a package called nibabel. I'm going to be doing some numerical manipulation using everyone's favorite Python matrix manipulation software, NumPy. I'm going to also be doing some plotting in 1, 2, and 3 dimensions of the MRI using matplotlib, Seaborn, and Napari. And thank you very much to Dr. Freda Vertiger for putting me onto Napari. It is very, very wonderful, as hopefully I will sell you on it later. On top of that, we're also going to make sure that our image voxel intensities are nice and homogeneous by doing bias correction. We're going to be taking a neural network and applying it to a neural network when we do some brain extraction. And also we're going to be doing some basic tissue segmentation. So dividing the brain into a couple of different tissue types that it's made up of. So gray matter, white matter, and hopefully cerebral spinal fluid and the background. And we're going to be doing that using sklearn for those folks who are a little bit more familiar with the area. When I say segmentation, what I'm really meaning is basically clustering. And then we're going to be taking our brain image and smushing it into a sort of standardized space, which allows for these group comparisons to occur. All right, so that then finishes the tutorial portion of this presentation. So here we are, just in everyone's favorite go-to when working with Python, just a Jupyter notebook. And as you can see, I'm just importing the usual suspects, so NumPy, Pandas, and Matplotlib. sklearn, I don't think that needs an introduction, but I'm also importing some very specific neuroimaging tools here. So first up is nibabel. So nibabel, as the name suggests, allows us to read in a particular kind of imaging data called NIfTY. NIfTY is basically just a standard form of the data existing, which contains a header and the actual data existing in a single file, which is very nice and very wonderful to work with. So we're using nibabel to read in the data and do some basic manipulation, so some rotatey stuff. I'm going to be using NiPipe. So NiPipe is a library which is primarily designed for creating imaging pipelines, so taking raw data and walking away and coming back several hours later to nice pre-processed data, and also wrapping various neuroimaging libraries into Python as well. But tonight I'll just be using it to do a little bit of rotation as well. And then I'll also be importing ants and ants PyNet. So both of these are from the same group, and these are absolutely fantastic libraries for spatial manipulation of MRI data. On top of that, ants will allow us to do bias correction, so sort of get rid of any weird shadowing, which is occurring based on the inhomogeneities of the magnetic field. And ants PyNet, as the name suggests, is a library which houses specially trained neural networks to allow us to do a whole bunch of different things to our brains. And in this case, we're going to be using ants PyNet to extract the brain. And then outside of the usual suspects of visualization, I'm going to be importing Napari. A very brief overview, because there is a lot to sort of cover. Napari is a wonderful GUI-based piece of software, or GUI-based library, which takes raw NumPy arrays and presents them in 2 or 3 dimensions. There's a whole bunch of rendering options, but the thing that I really do like about it is not only is it incredibly fast and incredibly responsive, but it also allows for alteration of code on the fly, and those changes are then popped into the viewer object, which then allows us to sort of look and monitor changes that we've made in real time. So once again, just to have a very, very quick overview of what we're going to be doing: loading the NIfTY data, manipulating the MRI image. We're going to be doing bias correction. We're going to be creating a brain mask. We're going to take the brain out of the skull, not literally, digitally. We're also going to be doing some tissue clustering and mushing the brain into a standardized space. And hopefully along the way, we're going to have some laughs and we're going to have some fun. All right. So to begin with, I'm just going to load in the data itself. So the NIfTY file is somewhere about 40 megs. The reason that it is 40 megs is because it's compressed. If it wasn't 40 megs, it would be, if it was uncompressed, it would be somewhere about 120, 130 meg per image. So all I've done is loaded the data using nibabel, and nibabel returns an object which contains the header information and the data sort of smushed up into one wrapper. But what I really want to do is just get directly to this data and have it existing in a NumPy array. And that's exactly what I've done here. I've taken the data out of this NumPy object and popped it into a NumPy array and just printed out a couple of metrics for us. So the image that I'm going to be working with tonight is of dimensions 256 by 256 by 176. So thinking about that spreadsheet analogy, it would basically be a spreadsheet which contains 256 rows by 256 columns, and there's 176 of these spreadsheets stacked on top of each other. When we take all of these individual voxels and lay them out end to end, there's actually 11,534,336. So it's big data in the way that it's not really big data because it fits in RAM, but big data because it's a lot to mentally keep track of. For this image as well, it's been acquired at a resolution of 1 millimeter by 1 millimeter by 1 millimeter. So each voxel contains 1 millimeter cubed worth of brain information. The image itself has intensity values ranging from 0 to 1,933, but something to keep in mind when working with scanners, this isn't sort of a uniform intensity range, and this can vary from scanner to scanner. It can actually vary from hour to hour. So kind of take the intensity values with a grain of salt. And they desperately will need to be manipulated or standardized in a form. So just to plot the image using matplotlib, here we go. That's the image that we're after. What you can see is I've basically just created a standard subplot. I've taken the NumPy data and I'm plotting the 125th slice of our image, and that brings up this happy fellow. Now, the reason that I had to do rotate 90 on the image itself is otherwise the head would kind of be existing out of the y-axis, and that's just not particularly good. On top of that, we can plot multiple slices at once. So there we go. This is sort of 3 different orientations of the brain, or 3 different sort of perspectives on the brain and on the head and neck, excuse me. And so as you can see here, we're plotting the 125th slice from the first dimension, the 100th slice from the second dimension, and the 100th slice from the third dimension. And here I've got some how the actual dimensions progress as numbers increase. So for example, in the first dimension, going from low to high will move you from the front of the brain, or front of the head, backwards to the back. Here we have going from the bottom of the image, or the inferior portion of the image, all the way to the top of the image, or the superior portion. So from the neck up to the tippy top of the head. And then here we're moving through the brain from the left ear through to the right ear. So while this is a perfectly workable system, I'm quite used to working with my data in a more sort of particular form. So I'm going to reorient it using NiPipe to a form called RAS, where the first dimension moves from left to right as numbers increase. The second dimension moves from inferior to superior as the numbers increase. From posterior to anterior as the numbers increase. And the third dimension moves from inferior to superior as the numbers increase. And all I'm doing, quick, simple, and easy, I'm taking my data, reading the data in, reorienting it, and then loading in the data, extracting to a NumPy matrix, and then plotting it out. And there we go. So as you can see, it's now in RAS orientation. So left to right is 176 slices, anterior to posterior is 256, and inferior to superior is 256 slices as well. So that's sort of the first basic part done. That's the hard part done, right? We've read the data in, hooray! Except now we've got to do some manipulation of the image to actually make it workable. So taking a look at the image here, for example, we can see that there's sort of a shadowing existing at this more superior portion of the brain and of the image. And that's not really what we want. What we want is a nice homogeneous intensity value. So all of the gray matter volume voxels, for example, exist within a particular sort of data range, and all of the white matter voxels exist within a particular data range. So in order to fix this up, we're going to have to do something called bias correction. So how does bias correction work? Well, long story short, there's several papers on it, and there is not really a huge amount of time to go into it. But there are multiple papers on it, and it's called N4 bias correction. It's a fun read. So the first thing that we notice about these images, though, is there's a lot of black. So this black is pretty much just indicating zeros in our data. So for those of you who are used to kind of dealing with this sort of information, what we could do is we could take our matrix and make it into a sparse matrix. So just sort of ignoring everything that is zero, except what you can't see is that it's not exactly zero. There's a whole bunch of noise existing in this image. So the black kind of ranges from about 0 to I think about 90 in terms of intensity. So the next best thing that we're going to do is just create a brain mask. And I'm telling NumPy, okay, create a Boolean mask. And so anything above an intensity of 90 is going to be sort of what we're interested in. Anything less than that, we don't care about. And then turn it into a binary mask. So just make it 0, things we don't care about, 1, things we do care about. And plotting it, this is what our brain mask looks like. Now we're going to take this brain mask and then we're going to apply it to our brain in a bias correction function. And what this is going to do is a couple of things. Number one, it's going to help with bias correction around sort of the edges of the brain or of the head. But on top of that, it's also going to cut down on computational time because there's less information that this function needs to correct. So taking a look here, what we need to do is first take this NumPy mask, convert it. There's a theme for tonight, and the theme is lots of conversion. So we need to take this NumPy array, we need to convert it into a nibable format. We then, because we're using ants for our bias correction, need to take that nibable format and transform that into a format that ants is able to use. I don't know why the folks at ants didn't decide just to go with nibable format, but at least they were very kind to give us this function here, which allows us to very quickly and easily transform. So transforming the data, transforming our mask, and transforming our RAS rotated data into this ants format, and then we're going to apply the bias field correction. So that should take all of about 17 seconds. And as you can see, sort of ticking up here, hopefully, it's an iterative approach. So it's basically just going from finer, going to finer and finer segments of the data as well. And we're nearly at 50, okay. So a little bit more than 17 seconds today. Cool. 22 seconds. I probably shouldn't have something running in the background while I'm doing this, but that's okay. We're then going to take that and take that bias corrected image and extract the NumPy data. And so on the left, we have our original image. And as you can see, it's got that shadowing existing. But then taking a look at our bias corrected image, we can see that the voxel intensities lower down the image and at the top of the image are pretty much identical, which is exactly what we want, because we don't want to have, say, a classifier looking for voxel intensities between, say, 100 and 200 to be white matter and everything else to be something that we don't care about, and having 100 to 200 down here, but then having 50 to 90 up here. That really wouldn't work too well. So what I'm going to do is give us our first look at Napari. There we go. So I've just opened up Napari, and as I said, it's a GUI-based system, which allows us to nicely, very quickly scroll through this bias-corrected image of the brain. As we can see, sort of all of the voxels have a nice homogeneous look about them. So white matter all looks to be the same kind of intensity value. Gray matter all seems to be the same intensity value, which is very nice and pretty.
Hey, Peter.
Yeah.
Is there meant to be a little like UI element that you're exploring right now?
There is. Is there?
It's not coming up on the Zoom share.
Okay. One moment. I apologize about that.
No, that's right. You can never quite tell what things it's going to show and what things it's not until you're doing it.
All right. So in that case, there we go. Have unfettered access to the entirety of my desktop.
There we go. Nice.
Cool. All right. So this is Napari. And as you can see, it's a nice GUI-based software, which allows me to very quickly and smoothly scroll through this three-dimensional array in 2 dimensions. But I don't want 2 dimensions. I want a nice, pretty rendered picture, which is what we all came for. So I'm just going to click this button, and hello, that's a familiar looking face of nightmarish proportions, which is what MRI does for everyone. So as you can see, this is now a fully rendered 3D image with just a simple click of a button. And we can just transform between 2D and 3D super quickly and easily. All right. So what we want to do is we're really quite interested in looking at changes that happen in the brain, for example, and diagnosing pathologies that occur in the brain itself. You know, sometimes it might be interesting to look at, say, the cheek, but for example, stroke, we're not really interested in what's going on in the cheek, we're interested in what's going on in the brain. So the first thing that we might think of if we're just interested in the brain is, okay, why don't we just sort of create a really basic filter where we say anything that is less than or equal to this particular value is brain, anything other than that is not brain. So what we're going to do is just very quickly take a look at how that would work. So I'm going to say anything that is greater than, say, the 25th percentile onwards of intensity values is going to be brain, and everything other than that is not brain. So if we run that, we should now see our overlay occurring in blue. And we can already tell that there's a huge amount of overlap of intensities from things that are brain to things that are not brain. So we can't just do a simple thresholding mask to pull out the brain from the not brain. So what we need to do is something slightly fancier, and we need to do brain extraction. Now, brain extraction algorithms have come a very long way over the last 2 decades, to be honest. Oh God, it's very disconcerting thinking about that. They've come a very long way over the last 2 decades, where they started off as algorithmically algorithms, and now we're sort of moving very heavily into the wonderful world of neural networks and specially trained neural networks to do various things with imaging. They've very much been a game changer. But it is still early days with them. So largely they're relegated to doing fairly simple things like replacing algorithms replacing algorithms and doing some very quick adjustments to images, which nicely dovetails into this function here, which is brain extraction, which is part of the Ants PyNet library. So this is a specially trained neural network, which has been trained on T1 images, so the same image that we're using throughout this presentation. And what it'll do is it will basically go and assign a probability value to each voxel, and this probability value will be either you are brain or you're not brain. So 1 means definitely brain, 0 means definitely not brain, and 0.5 means So what we're going to do is we're going to run this brain extraction network on our data. We're going to convert our data to Yep, there we go. We're going to convert our data to, why am I doing it on the, that's fine. We're going to convert our data to ants and basically make everything happen. So there we go. I'm taking a threshold of, I'm taking that probability map. I'm then taking a threshold of a probability of 95% or above, and this has nothing to do with an alpha value, by the way. Just 95% probability gave me a nice extraction mask. And then we're going to extract that mask and turn it into a binary mask, turn it into a nifty image, or a NumPy image, sorry, a nibable image, and then we're going to plot it. And we're going to see how it did what we want from a good brain extraction mask, which we're then going to use to extract the brain, is for it to be overlapping quite nicely with the brain itself. So the mask is going to be shown in red, and in gray we have the underlying bias corrected image. And as we scroll through, we can see that largely it does a pretty good job. So keep in mind that this neural network extracted this brain, or created this brain mask, or the probability map, sorry, in about 17 seconds. Compare that with one of the most widely used brain extraction algorithmic methods called BET, which is a very, very fine tool, I need to stress. But the thing with BET is that would probably take about 2.5 minutes. So it doesn't sound like very much for a single image, but when you're dealing with tens or thousands of images, this tends to take a lot of time. So very quickly scrolling through, we can see that the brain mask quite nicely actually hugs the contours of the brain. It doesn't sort of chop off any giant bits. But one thing to take note is it's clearly not perfect, because the brain mask is escaping a little bit from the cerebellum region and calling a little bit of the interior of the skull and also the exterior of the skull slightly into the neck as brain. In theory, we could fix this up manually, but in the interests of time, I'm not going to bother doing that. Speaking of BET, so here is BET's brain mask. So BET is in blue and the neural network is in red, and obviously any overlap between the two is in purple. And looking through, we can see that the BET solution consistently overshoots the brain and also chops off a very large portion of this frontal lobe. So, look, in terms of its performance, it could be better, and I could probably get better performance by twiddling knobs and doing a whole bunch of things. And there'd also likely need to be some manual changes to the mask as well. So really, I didn't know that neural networks had been specially trained until earlier on this year, and I'm very much never going back, to be completely honest. All right, so we've got our brain mask, which nicely hugs the brain, and then all we're going to do is take this brain mask, extract, basically use NumPy to say, hey, anywhere that there's a 1, just get me the index of that, create a bed of zeros in the same dimension as our original brain. And then we're just going to take these coordinates of our existing brain from the brain mask and pop them into that bed of zeros, and then convert it into a nibable format. And here is the end product. There we go. So the mask is overlaid is red, and the original brain underneath is in gray. There we go. So we've now successfully removed the brain from the skull with no muss and no fuss, and absolutely no surgery involved, which is very impressive. And just to very quickly, once again, showing off the 3D rendering capabilities of Napari, this is quite a nice extraction. So there doesn't seem to be any sort of meninges or outer coating or outer covering of the brain. to obscure our view of the sulci and the gyri. So the sulci is sort of the outy bits, and the the gyri are the outy bits, and the sulci are the inner bits of the brain, the foldy bits. So we now have our brain, which means we can go and we can perform some fun little things on it. So the next thing we're going to do is we're going to segment the brain. So when I say segment, once again, all I'm going to do is do some clustering. Now, we have a three-dimensional image, and a lot of standard clustering methods don't like three-dimensional data. And they will happily work with two-dimensional data. And so that's exactly what we're going to do. We're going to take our extracted brain. We're going to then use the NumPy ravel function to literally take the brain and sort of take each voxel and lay them out one by one until what we have is just a nice single dimensional array, or we've got an array. So we go, we do that, we wait patiently as it takes our three-dimensional image and deconstructs it into an array, and then we'll plot it with a histogram on the left and just a slice, because the histogram looked kind of boring, on the right. And so with the histogram, we can see that the image is absolutely dominated by zeros. So there's a huge amount of zeros in this datum. But what we would hope to see is also there would be varying intensity values. So maybe a bimodal or even hopefully a trimodal distribution existing throughout the brain, which we could then potentially say, right, from this value to this value is gray matter because it's got a higher intensity. From this value to this value is gray matter, and this value to this value is say cerebral spinal fluid or background. So let's see how that looks. So I'm going to plot the same histogram, but this time cut out all of the values that are zero. Now, going back to an earlier point, you might remember that I said that there was a whole bunch of noise which existed in this black part. We've gotten around that by extracting the brain and just popping it into a bed of zeros. So now the background really truly is zero. And looking at the histogram, we can see that, oh, look, there is actually nicely a bimodal distribution. So in theory, our hypothesis holds that we might be able to just take various intensity values and segment those out based on particular intensity values. The first thing that we're going to do, though, is we're going to take this flat brain and we're going to reshape it. And so what we're actually going to do is, for this single brain, we're going to create a one-dimensional matrix. So off we go, we reshape this flat brain, and there we are. So what is basically going on is each pixel value exists in its own separate row in one column. So printing out the shape, we can see that there's the 11.5 million of them with a single column. So what I'm going to do is there's a couple of ways that we could potentially cluster this image. We could use everyone's standard go-to of k-means. We could, because this has a kind of Gaussian-ish shape, we could potentially use a Gaussian mixture model to try to extract or try to fit Gaussian-based distributions to this data. But I think, to be honest, I did play around with using a GMM and found that its performance was lacking for some particular reason. So I decided just to use everyone's favorite go-to for clustering of k-means. Now, this talking has been a nice segue because k-means is going to take the longest out of this entire presentation of about 1 minute. Oh, look, it's done. But what I've done is I've asked k-means to extract me out 4 particular clusters or 4 particular pieces of information based on the image. So what I'm hoping to get is something that outlines the white matter or the telephone parts of the brain, something that outlines the gray matter or the thinky bits of the brain, something that outlines the cerebral spinal fluid, so the liquid that the brain floats in and gains nourishment from, and the background itself. So if we scroll down to here, where I've handily gotten a plot going, there we go. Here's our original image on the left, or here's our original slice, sorry, on the left, and here's the k-means extracted information on the right. And you can see that we do actually have a nice segmentation of the background. We have this white matter existing in blue, we have the gray matter existing in green, and we've got the cerebral spinal fluid, thankfully, existing in the yellow image. So that was pretty cool. And it didn't take much time at all. And just to show you that it did actually apply to the full three-dimensional brain, we can now scroll through. I kept meaning to change that. There we are. We can now scroll through and see that this has done segmentation or clustering over the entire three-dimensional image. What I've done is I've taken that output of the one-dimensional predictions and then just reassembled them back into a three-dimensional form. Okay. So we were attempting to make some sort of prediction on our data. So we could basically look at each section of this histogram and say here to here is white matter, here to here is gray matter, and so on. And we can see when this eventually plots, and there we go, this nice multicolored histogram, that that's exactly what we've got. So the lines here represent the means of the k-means algorithm. And we can see that what the k-means has actually done is it said, you know, look pretty close to the peak of this histogram, that from this voxel intensity range of, I think, about 500 to 600 plus is white matter. This intensity range from 500 to about 350 is gray matter. And then sort of as we move down, we've got the CSF and the background. And look, to be honest, that's not a terrible output for something that took all of about a minute and a half. All right, so I realize that I've been talking now for 38 minutes and some folks might be getting a little bit bored of hearing my voice, but I'm just gonna ask, so there's one more section to go. If, Ned, would you like me to sort of continue on to this mushing the brain into a standard space, or would folks like to see some really pretty pictures that other folks have made?
I mean, I feel like this has been a pretty awesome narrative so far. I'm keen to hear the end, and I suspect other folks might be too. So why don't we see the brain smushing?
All right. So unfortunately, I wish that the brain smushing is actually a nice sort of infographic of taking brains, mashing them together. But like most things, it's just going to be a mathematical transformation. Sorry. But we're going to try to make it fun. So working with the data so far, it's been in a very particular space. So it's been in what's called subject space. So it exists in its own coordinate system. Now, this is all very nice and well when we're working with a single image, but what we want to do is we want to take our images and we want to transform them so they're all existing in the same kind of space. And so, for example, you know, transform them so the frontal lobes overlap with the frontal lobes of everyone else, and the temporal and parietal lobes overlap with the temporal parietal lobes of everyone else. But we want to keep the uniqueness of each individual brain. So it's a little bit of a tricky proposition, and we do lose some of the uniqueness of the brain through mushing them into a template space, but largely it beats the alternative, which is doing region of interest across 11 million voxels. So the first thing that folks have actually come up with is a whole bunch of standardized template spaces. So I'm going to be using Canada's favorite template space, the Montreal Neurological Institute's 152, or MNI for short, template space. There is a template which already exists, which I'm going to be loading in using Nibabel. I'm going to just make a quick brain mask of it. just in case we do need it moving forward. But then what I'm going to do is also take our existing extracted brain, convert it from naive form into ants form, and then I'm going to apply an affine transformation to it. So an affine transformation is going to take the image in subject space. It's going to rotate it in X, Y, and Z coordinates. It's going to also translate it, so sort of shift it around this three-dimensional space. It's also going to stretch it out a little bit, or maybe sort of squish it in a little bit. And eventually, because it's basically going to be going through iterations to try to get the best possible fit, we'll have something that has gone from a subject space into a template space. Now, running this, and it's done. Running this, I would just like to very, very quickly say the reason that this is going on so fast is because I'm just using what is called a simple affine transform. Now, affine is sort of the second lowest form of quality that you can get when smushing brains together. Arguably, the sin or sine method, which comes with ants, is the best, but something tells me that a whole bunch of folks wouldn't necessarily want to be on the line as I waited for 25 minutes for this to complete. So I've taken the brain and I've warped it from subject space into template space. And now I'm just plotting in Napari two things. I'm going to plot the template, and on top of that, I'm going to plot the original subject space brain in red. So as you can see, they are in no form actually aligned. But on top of that, the subject brain or the normal brain actually is of quite different dimensions to this template brain. So they are not the same thing. Unfortunately, there's no overlap, which means any sort of group analysis, clustering, or regression that we might want to do is not exactly going to be worthwhile. But then overlaying in blue our warped brain, we can see that by and large, it's a pretty good fit. And I'll just click that little eye to hide the subject space. So we can see that by and large, it's a pretty good fit. There are some issues around this frontal region, for example. There's some issues around the cerebellum or the posterior of the cerebellum and sort of this region around the parietal lobe. I think it's the parietal lobe. My partner is significantly better neuroanatomist than I am, so I will defer to their judgment. But look, for 17 seconds, it's not bad. It's not bad at all. And also for this talk, it is very good. So what we've done is we've taken our image from from subject space, we've smushed it into a template space, and we've not only gotten the output brain image, but we've also gotten some forward transformations, which means that anything else that is also in our subject space, we can then go and apply these transformations to, which we're just going to be doing in ants yet again. And that will take it from subject space to template space directly without having to do any of the iterations. Okay, so we've just done that, quick, simple, and easy. And we're now going to plot in Napari once again. There we go. So here we have our clustered brain tissues overlaid on top of the MNI image. And so as you can see, it's not done a particularly terrible job. I mean, again, it's not brilliant, but for 17 seconds worth of computation of a three-dimensional image, I'm not going to complain. And so then what we can do is we can sort of take this image, we can go and extract information from our template space image. We can go and run group analyses by stacking all of the images on top of each other and running a voxel by voxel analysis. So kind of think like doing a single t-test only 11 million times. We can go and do classification because now we know that all of the different portions of the brain are going to be in the same space. So that is pretty much a very, very quick rundown of working with MRI data. But once again, before it ticks over to 7 o'clock, I just want to outline what we went through today. So we loaded in the MRI data. We did some basic manipulation, so creating brain masks using NumPy. We did bias correction of the image to get rid of any shadowing. We created a brain mask itself, and we using a neural network, and performed skull stripping just by using some really basic.
Oh no, I think we've lost Peter, at least on my end.
Yeah.
Mm.
Oh, Peter's back.
Hey, Peter's
Hello.
back. Hey.
Sorry, that was an incredibly fortuitous place for my internet to actually drop out. So yeah, there ends the talk. Sorry.
Do you yeah. So does anyone have any questions for Peter?
Well, yeah, so I was just saying, like, NumPy seems like it's pretty new. It just came out last year. So what did people do before? Like, just not have 3D? Like, I mean, the data's 3D. So you didn't look at it in 3D? You just...
No, not at all. We actually, there's multiple viewer software available for MRI. But because I wanted to keep it fixated on Python itself, I didn't talk about them. But you know, if you're interested in looking into them, for example, there is one written predominantly in Python called Fossilize, or FSLIze. That is a pretty good go-to for a three-dimensional visualization. There's also in MATLAB a toolbox called SPM, which allows for three-dimensional visualization as well.
Oh, cool.
But I do highly recommend Fossilize.
Anyone else have any questions? Greg.
Yeah, when you were going through the NumPy and sliding along manually, it looks like there's a play button. Will it do the animation for you?
It will. But I'm a little bit of a control freak, so I need to, you know, nicely scroll along like that rather than having the computer to tell me how fast it can scroll.
All right, thank you.
One question I had was, we were sort of talking about when you jumped off, that looking at the ants GitHub, it seemed like it, given how amazing what it does, like it sort of only had, I don't know, 600 stars or something. And so there was sort of an interesting question about, I mean, you know, obviously it's a niche tool, but I mean, I guess, I don't know, what could my question might be, what sort of reach does it have in the sort of the community of users? Like, how established is it? And then I guess as a secondary question, do you think work on that sort of tool in this particular scientific community is, you know, recognized? Because I know more generally, you know, in science, in particular where there's software involved, you know, it's all about publish, and it's not always the case that you can get recognition for software. There are some specific journals, but they're quite few for getting that recognition for software. But yeah, is that a challenge in this particular field?
Sure. Well, look, I'm not going to pretend to speak for the creators of ants, but one of the things is it's actually quite recent that a whole bunch of established imaging software has sort of shifted off and opened up their own GitHubs and sort of opened themselves up to open source production. Which is possibly a reason why, you know, there's only 600 stars for it. But at the same time, 600 stars in an area which is actually quite swamped. So there's a whole bunch of different solutions for doing the image manipulation. You know, it is a reasonable sort of thing. Also, ants. Let me put it this way. There's a lot of different competing software packages out there, and they're all not doing it for the dollars, they're doing it for the academic cred, which, you know, as a survivor of academia, I'm sure you can understand is far better than dollars in the wallet. In terms of recognition, so yeah, look, these the people who've actually made ants have gotten a whole bunch of not just publications out of it, but also they've won awards in, you know, very, very niche areas of imaging manipulation. That being said, it doesn't necessarily have to just be for medical images. So ants actually have a very nice tutorial. They don't suggest you do it, but you can do it. They have a nice tutorial where they basically take, you know, 2 pictures of cars of completely different shapes and warp those cars, warp one of the cars into the shape of the other one, not losing any information. So in theory, these tools can be applied to uses outside of neuroimaging.
Yeah, cool. That's awesome. Yeah. No, I mean, and I think you're right. Like, I know I feel weird about continually to talk about the number of stars, but that is like actually for such a niche community. Like, I think that does make sense. It's like I'm a bit primed from coming from sort of open source dev tools and things where it's, you know, it's always in the thousands or whatever. And but yeah. Any other, one more question before we jump off, or sorry, before we sort of move on to the next bit? Anyone else? Cool. All right. Well. Okay. Go, David.
Not really a question, but could you do your summary, like the conclusion, just say it for the YouTube video? So Ned can like copy paste it to where you dropped out.
Yep, of course. Are we still recording, or?
Yeah, we are.
All right. So in that case, the delayed outro is we've basically now gone and we've taken our data, we've loaded it into Python, we've done some basic manipulation using NumPy in creating brain masks and done some basic rotation on it. We've bias corrected the data to get rid of that shadowing that exists because of inhomogeneities in the magnetic field. We have used a neural network in Ant's PyNet to extract the brain and create a brain mask, actually, and then used some very basic NumPy indexing to extract the brain itself. Furthermore, we did some tissue segmentation or tissue clustering and transformed our data from subject space into a template space. One thing that I did forget to mention at the beginning of this talk is that this will all be existing on my GitHub fairly shortly. So people can more than happily go and have a play around, and I'm sure that Ned will pop a link somewhere, possibly on the Twitters or the LinkedIn's ?
Sure can.
Fantastic.
Yeah, thanks so much again for that, Peter. That was amazing.